All right, the geometric series test. Now, as you've probably observed, the word geometric series is one you've been seeing since Algebra 2 or pre-calc, whenever you first learned about series. And these are yet, in fact, those geometric series. So the just to remind you, a geometric series is a series or a sequence where to get from one term to the next, you multiply by something. So for example, 1 plus 1/2 plus 1/4, the one that we've seen many times by now. This series, to get from one term to the next, was keep multiplying by 1/2. And the formula would just be 1 over 1/2 to the n, where n starts at 0, because 1/2 to the 0 would be 1, 1/2 to the first power would be 1/2, 1/2 to the second power would be 1/4. Oops, this should be 8, not 3. So the point is, though, that each one of these successive terms is going to have a higher power of 2 in the denominator. So that's what a geometric series is, separated by plus signs, obviously, because it's a series, not a sequence. And the basic test is that it turns out that geometric series always converge, the sum, in the calculus sense, converge, if r is less than 1. So this one converges. We've already shown that in a couple of videos in this chapter, that this adds up to 2. If we had 1/3 to the n, that would add up to a different number. But and then if you want to know the sum of a geometric series, you just use this formula. So you take the first term. So in the case of this one, our first term is 1. And then you divide by 1 minus r, which is the number you're multiplying by to get between terms. So since in this one, we're multiplying by 1/2, it's 1 minus 1/2. The reason I bring this up, and the reason we're going to review geometric series, is because these are kind of a trick question in calculus. Because if they give you a sequence, and maybe you were able to determine that it doesn't diverge by using the nth term test, but you want to know if it converges or not, and they might even want to know what the sum of the series is, like what number it's converging to, then if you have a keen eye for the geometric series, and you notice, hey, wait a minute, there's like a fraction raised to a power of n somewhere in the formula for that series, then you should know, you want to just be able to spot like, hey, that's a geometric series, awesome. I know that it converges because r is less than 1, and I can even figure out what it converges to by using the classic sum of an infinite geometric series formula. Pretty cool. So that's why you want to keep your eye out for this, is that anytime you're looking at a hard, they might just put one of these in amongst other harder types of questions in like the ratio test chapter or section or something on the test. But if you spot that geometric series, it's like, hey, that's easy, awesome. Let's move, I know I got that one right. And by the way, the reason that this is absolute value of r is because you could have a negative value of r, like negative 1/2. So if we had an r of negative 1/2, it would have gone 1 minus 1/2 plus 1/4 minus 1/8. And this is also going to converge, but again, r needs to be between negative 1 and 1. So it's got r basically has to be a fraction for things to converge. All right, let's take a quick look at one. Actually, we just did this. So just a second ago, I showed you that this adds up to 2 by using the sum of an infinite geometric series. But there's another fun way to prove this that some teachers are kind of keen on, and that is this. Let's say we wanted to figure out the sum here. So we'd say, well, hey, you know what? The sum is just going to equal all this stuff, right? But then what we can do is we can divide both sides by 2, or multiply them by 1/2. So I'm just going to take this equation that we have here, s equals this sum, I'm going to multiply by 1/2. So on the left, I'll just get 1/2 s. And on the right, I'll just get half of each term, right? So that 1 times 1/2 is going to be 1/2. And then 1/2 times 1/2 is going to be 1/4. And then 1/4 times 1/2 is going to be 1/8. And then 1/8 times 1/2 is going to be plus 1/16, etc. So all I've done is multiplied this whole top line by 1/2 to get this bottom line. And now we're going to use the old algebra trick of subtracting equations. If I subtract the left-hand side, I just get s minus 1/2 s, so I get 1/2 s. And on the right, this 1 doesn't have anything to subtract from, so I still have a 1 over here. But everything else cancels. 1/2 minus 1/2 is 0. 1/4 cancel. 1/8 cancel. There's obviously 1/16 that would have been here that cancels. And of course, all the smaller terms also cancel one against another. So 1/2 s equals 1. Pretty cool. Now if I want to solve for s, I just multiply this whole thing by 2, and I get s equals 2. So that's kind of a fun way to prove this, and we could use that for almost any geometric series. So if we had a series equals, 1 plus, if we had r equals 3, 1/3, so 1/9 plus 1/27, all we'd have to do is multiply by 1/3. And the same thing will happen if we subtract these two. That cancels that, that cancels that, that cancels that. And we get 2/3 s equals 1. So now to solve this, we have to multiply both sides by 3/2, and we get s equals 3/2. So that's kind of a fun way to find the sum of a geometric series using sort of algebra techniques instead of that infinite sum formula. Truth is, though, usually you'll use the usual formula, which is just find r and whatnot. So on this one, let's try and find the sum. Now, I've shown you this before. This adds up to 0.11111111111, just one repeating. But if we want to find the sum of a geometric series when it's given in this kind of weird form, a lot of times the smart thing to do is to put it in sort of like sigma notation, because a lot of times that'll be a step that the teacher wants you to do anyway. So what we'll do is figure out, hey, what's r here? Well, r is 0.1, right? Because if you take 0.1, multiply by 0.1, you get this. Multiply that by 0.1, you get this. So it's just 0.1 to the n, right? So easy peasy. So now that we have this, we can just plug and chug through the sum formula. So the sum of this geometric series is going to be it's just a1 over 1 minus r. So the a1, the first term, is 0.1. And 1 minus 0.1, r is 0.1 also. So that's 0.1 over 0.9. If you multiply top and bottom by 10, you get 1/9. Alright, so pretty good. So if you have a geometric series, you just want to figure out what r is, figure out what your first term is, plug and chug through the sum formula. This one's going to work really similarly. Looks like our work's already done for us. Let's just find the sum. So sum equals, now we need the first term. So all I do is I take whatever n is starting at, like in this case it's 1, and just plug it in. So the first term is going to be 23 over 100. And then I need 1 minus r. So what is r in this case? Well, let's see. If I list out my terms, and the key here, when you're looking at a geometric series, the way I know this is a geometric series is because I have something raised to the n, a number raised to the n power is usually the giveaway. So, but if I list out these terms, I get 23 hundredths plus 23 10,000ths plus 23 100th cubed would be a millionths. Or if you want to write this in decimal form, it's 0.23 plus 0.0023 plus 0.000023. See the pattern? This is 0.23 repeating. So what is my r? My r is not 23 hundredths because the 23 does not have a power of n, right? So the 23 is not getting raised to a power each time. The only thing that's getting raised to a power is the 100 to the n. So we could rewrite this as n equals 1 to infinity of 23 times 100, 1 over 100 to the n. So it's really the thing that's being raised to the power of n, that's your r. So r is actually 1/100th. So you get 23 over 100 over 99 100ths. Hundreds cancel, and you get 23 99ths. So you can see the tricky thing on that one was spotting that it was a geometric series, and the way we did that was noticing that there was a number raised to the nth power, and that ends up creating this geometric type scenario. And then the second thing was figuring out what r is, because it can be kind of tough to spot, but r is basically whatever is being raised to the power. And the one big trick is that you got to recognize that if something is in the denominator raised to a power, like if we have 1 over 2 to the n, that's the same thing as having written 1/2 to the n. So because this 2 to the n is downstairs, your r is actually 1/2, not 2. So even though 2 is being raised to the n power, because that's downstairs, the ratio is actually 1/2, not 2. I know I said that 3 times in a row, but it's really important. All right, geometric areas in disguise. These two puppies are both geometric. How do we know? Well, so this one up top is probably the most confusing one because we have a 2 upstairs. Usually geometric would just have 1 upstairs, or at least the ones we looked at so far kind of did. And then what the heck is e to the n? That's an exponential, right? So it kind of freaks you out and it makes you think, oh, that's weird. Let me see if I have some other rule for that. But e is really just a number. It's like pi. It's 2.7 something. Can't always remember all the digits. But if you want to look on your calculator, if you just use second and then e to the 1 and hit enter, it'll give you the decimal equivalent. And it's 2.7 something. So the point is you could rewrite this as 2 over 2.7 da 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 to the n power. So does that look more like a geometric series now? Because we've got a number raised to the power of n. And no other n's anywhere. If there had been an n factorial in here or something, or an n squared, now we'd have a problem. Now we'd have to use one of those fancy tests like the ratio test or something. But since there's just a number raised to a power of n, that's the tip-off that's probably geometric. And then if you really wanted to be sure, you could write out some terms. So we'd have, looks like the first term is 2 over e. The second term is 2 over e squared. The third term is 2 over e cubed. So you can get the sense here that we keep increasing the power of e by 1, which means that our r, what we're multiplying by to get from one term to the next, is 1 over e. So if you multiply by 1 over e, that's just going to increase the power of e downstairs. All right, so at this point we have enough information to plug in the sum formula, which would be the first term, which is 2 over e, divided by 1 minus r. All right, so you can see there's a complex fraction. It's going to get messy. Actually, maybe I just multiply top and bottom by e. So we'll end up with, come down here. So if I multiply top and bottom by e, that cancels that, and I just get 2 upstairs. And then downstairs, I get e minus 1. So kind of a wacky sum. Not obviously, it's obviously not a round number or anything, but the point is it was geometric, and everything worked out. So this one's going to be tough to spot, and technically speaking, this is not a geometric sequence or geometric series, because if you write out the terms, you would get 1 plus 3, which is 4 fifths, plus plug in n equals 2, you get 1 plus 9 is 10 over 25, which is like 2 fifths. And then your next term would be 28 1/25. Anyway, this gets messy. It's not technically a geometric series. But remember, when you're working these problems, usually what you're trying to figure out is if something converges or diverges. And if you recognize that it's kind of a hybrid of 2 geometric series, that's the trick. So if you want to rewrite this, this is really 2 fractions, 1 over 5 to the n and 3 to the n over 5 to the n. So we could just break that up into 2 separate series, 1 over 5 to the n plus the sum from 1 to infinity of 3 to the n over 5 to the n. And so right now you should be looking at it and saying, oh, I could see how that would be geometric, because in this first one we definitely have 1/5 to the n. That's pretty obviously what we said. There's a number raised to the power of n and nothing else confusing in it. So this is pretty obviously geometric. But this one is kind of weird. We have both 3 to the n and 5 to the n. What do I do about that? What we could do is just rewrite this one as 3/5 to the n. So if you have 2 things, oops, that's an n. If you have a numerator and denominator that are raised to the same power, you can just go ahead and put parentheses around that and just raise it to the exponent once. So these are algebraically identical, and when you make it a fraction raised to the power of n, then it gets really obvious that it's geometric. So even though the overall original is not technically geometric, you can still figure out the sum by breaking it up into 2 separate truly geometric series. And then also, because both these have a ratio less than 1, the ratio in this one is 1/5, the ratio in this one is 3/5. So because those are both fractions less than 1, they're both approaching 0, they both converge by the geometric test, the geometric ratio test, which said that the absolute value of r has to be less than 1. Therefore, this series converges as well. So that just keep an eye out for this complicated stuff. When you get in the harder tests, meaning the harder convergence tests, the sort of more advanced stuff in this chapter, you're going to start seeing really crazy looking things. But when you come across something like this, you just always want to keep an eye out for numbers raised to the power of n. Might be a geometric series in disguise.